Okay, so before I start, let me just first remind you that we're going to have our second midterm next Thursday, okay, on March 4th, I believe. And it's going to cover everything from lecture 9 to lecture 15. Lecture 15 is this Thursday's lecture. So topic speaking would include hash table, including basic about graphs, graph search, and the shortest path that we're going to talk about today and the next class. Okay. All right. So previously, we already in the first previous few lectures, we talked about basics about graph and how to perform graph traversal, graph search strategies. Okay. In particular, one of the graph search strategy, DFS algorithm, also has this nice property that it also gives us the shortest path distance in the input graph from the source node. Okay, but note that over there, so far, the graphs we are talking about are the so-called unweighted graph. Okay, and the graph can have weights both at vertices or edges. And today we're going to talk about this edge-weighted graph. We're going to talk about what is shortest path in such a weighted graph, and also going to introduce one algorithm to compute that, the so-called Bellman-Ford algorithm. Okay, so next time we're going to introduce yet another algorithm for shortest path in weighted graphs. That algorithm is more efficient, but only not for arbitrary graph though. Okay. All right. So what is weighted graph? Well, just to remind you, an unweighted graph, G, is just a pair, a collection of nodes, and a set of edges where each edge is a pair of nodes. Okay. So it's just a pair of B and E, node set and edge set. Okay. However, in general, when we talk about using graphs to model data, right, I mean, nodes and edges often carry precise meanings. Okay, so as such, they can also carry weights. The weights can mean a bunch of things. For example, in a transportation network, okay, now here, each node represents a city and the edge represents there's a road between two cities, okay? You can also have edge weights which reflect the distance between these two cities. Okay, so now so for example, the distance between San Francisco to Sacramento following this road is 95. Okay, so now this weighted graph not only give you connectivity information, which city are connected to which other city, it also tells you more. It also tells you that what is the distance it has between two cities if you follow this road. Okay, so this gives you richer information. Okay, and so more formally, here we're talking about the so-called edge-weighted graph, where it is edge-weighted graph is simply now a triplet. It has a collection of nodes, okay, and a collection of edges, and also an edge weight function, which is basically map every edge to a real value. Okay, so for example, in this picture, the weight of the edge from San Francisco to LA, that's this edge. The weight of this edge is simply 409. Okay, so every edge has a weight, that's it. So now an edge-weighted graph has three inputs: node set, edge set, and a weight for every edge. Okay, okay. And of course, the graph can still be directed or undirected. And also importantly, the weights can actually be both positive and negative. It doesn't have to be always positive depending on the applications. Okay, now the edge-weighted graph encode richer information and is useful in many applications. We already saw that in this transportation network now. We not only know that whether two cities are connected or not, we also know that what's the distance between them. If I want to travel along this path, along this road, what's the distance, how many miles I have to go, okay? And in a social network, you could, the weight of an edge connecting two nodes can also represent the strength of the friendship, of the connection between those two people. Okay, in the protein-protein interaction network where each node is a protein molecule, then the edge means that they may interact, and the weight of the edge can indicate what's the probability that this protein, when they see each other, they may interact. They may, okay? All right. So now in general, one can also talk about the node-weighted graph, where every node also have a weight, okay? It can also carry more meaning, but in this class, we're going to just focus on edge-weighted graph, which is very popular in practice. Okay. All right. So now we have a weighted graph. Now the length of a path is defined differently. Now we have to take the weights into account. Okay, so in particular, given any path in this graph, the length is total weight of all the edges in this path. Namely, you take the sum of all the weights of edges in this graph, in this path. Okay, so for example, if I consider the path from San Francisco, use a different color, from San Francisco to LA to Bakersfield and then to Riverside, then the length of this path, okay, this path has 3 edges, but now the length is not 3 anymore. The length is the sum of edge weights, 409 plus 112 plus 207, okay, which is 724. Okay, all right. So if we consider another example, let's say that if I consider the path from Los Angeles to Bakersfield and then to San Francisco, okay, then the length of this path is 112 plus 290, which is 302. Okay, so this is this path that we have. Okay, all right. But we could have another way. I mean, that between 2 cities, there are different paths to connect them, right? So for example, going from LA to San Francisco, I can also go this path. This path has only 1 edge, okay? And the length of this path is simply 409, okay? All right, now note that to go from LA to San Francisco, I have different ways, okay? This blue path has only 1 edge, okay? However, this edge is long, so the length is actually long. Why if I go the purple path, even though I have 2 road segments, but then the total length is actually smaller, which is only 302, okay? So if you are supposed to, if you want to travel from LA to San Francisco, which one would you take? And naturally, we want to take the one that is shortest in the total distance in length, okay? In other words, we are going to travel along this purple one, okay? So this also motivates the concept of shortest path. The shortest path from U to V in the way to the graph is basically the path with the minimal, smallest possible length, okay? So for example, in this example, even going from LA to San Francisco, the shortest path actually is going through Bakersfield and then to San Francisco, okay, because the total length is the smallest, okay? All right. Now here's another example. So in this picture, what is the shortest path from V1 to V6? So look at this, we say, well, an obvious path is going this way, and this one has length 7, okay? Or I could also go this way, and the length of this path turn out to be also 7, okay? Is this the best we can do? What do you think? Well, some of you may already observe that. Well, I could maybe go this way. First I get to V5, but then I follow to V7, and then from V7 go to V6, okay? And the total length, the length of this path is 2 plus minus 1 plus 1 plus 3 minus 1. So we get that the length of this path is only 4. So this, and then you can try, there's no shorter way. So this is the shortest path to go from V1 to V6, okay? So, all right, the shortest path distance. So now when we talk about distance in the way to the graph, we refer to that, we basically refer to the shortest path distance. From U to V is just the length of the shortest path from U to V. Okay, so in the previous example, the shortest path distance, the distance from V1 to V6 is 4. Okay, all right. Now, note that the shortest path may not be unique. There may be multiple ways to go from U to V, all have the shortest length, okay, but they all have the same distance. So for example, in this picture, if I consider V2 to V5, okay, I can reach V2, V5 this way, and the weight is 14. It's long, but I could also go this way. The weight is 11. and it turned out this is the shortest path. You cannot go from V2 to V5 in shorter lengths. Okay, but I have another path going from V2 to V6 and then V6 to V5. This one also have length 11. So I have multiple shortest paths going from V2 to V5. They all have the same shortest possible distance. Okay, all right. Now, earlier, we also talked about the shortest path, but there our graph is unweighted, okay? Or alternatively, you can view an unweighted graph to be a weighted graph where all the edges has the same unit weight, namely all edges has weight 1, okay? And because of this, what is the length of a path? Well, if all the edges has weight 1, then the length of a path, say going from here to here, is simply the number of edges in the path. That's how we defined this length earlier. Okay, so basically, the way we define length and shortest path, there's no contradiction. It's just there for an unweighted graph, we have treated where all the edges has weight 1. Okay. Now remember that for unweighted graph earlier, or where all the edges has weight 1, we said that DFS algorithm can compute the shortest path length to the from the source. There, okay? So in other words, you can think that the breadth first search actually can compute the shortest path distance from a source node for a graph where all the edges has unit weight, has weight 1, okay? But you can extend this to where all the edges doesn't have to have weight 1. They can all have weight 10 or any other weight, but as long as all the edges has the same edge weights, okay? Then the shortest path between two nodes is basically equivalent to the where the length of the path is measured by the number of edges inside. Okay, and as a result, the breadth first search algorithm can be used to compute the shortest path for graphs where all the edges has equal weights. Okay, so okay. But of course, this doesn't apply to general weighted graph. Like in this example, these edges do not have equal weights. Okay. Okay, now let's look at some properties of the shortest path in weighted graph. Okay. Note that because we allow the edge weights to be negative, okay, and it turned out that in general having negative weights is not a problem. However, if you have a negative cycle, then there's an issue. Okay, what is a negative cycle? A negative cycle is just a cycle whose length is negative. Okay, so for example, the one I'm showing here, going from U2 to U3 to U4 to U5 and back to U2. This cycle has weights -2, which is the length of this cycle is -2, which is negative. Okay, so this is a negative cycle. So why do we have problem when we have negative cycle? Well, the shortest path is no longer well defined. Why? Suppose you want to figure out what is the shortest path going from U1 to U6. Okay, now it seems natural that we should go this way. Okay, so this blue path has length 7. But is this the shortest? Oh, you realize that, hold on, because the cycle, the length of the cycle is negative. What I can do is that I can do the green. I can go here and then I go circle around the cycle and then continue to U6. So what is the length of this green path? That's basically 7 plus this cycle's length, which is -2. That means it's 7 minus 2, which is 5. So now we get a shorter path by going through this negative cycle. Okay, but is the green one the shortest possible? Well, no, not necessarily, because what I can do is that I can just come here and then repeatedly go through this negative cycle many, many times. Every time I go through this negative cycle, my total length reduced by 2 because the length of cycle is negative. Okay, so I can do this infinite number of times, and then my length can be minus infinity, which means that I do not have a shortest path from U1 to U6. Okay, so shortest path is no longer well defined if you have negative cycle, because you can just keep looping around in the negative cycle. Every time you loop around it once, your distance, your length becomes smaller. So you keep decreasing the length. Okay, so it's not well defined anymore. Okay, so when we talk about graph in shortest path, we assume that the input graph, it can have negative weights, not a problem, but it cannot have negative cycle. Or maybe we want to identify if there's negative cycle. If there's a negative cycle, we want to be able to detect it. Okay, to know that okay, in this case, the shortest path is not well defined. Okay, now suppose we are given the graph with no negative cycle. Okay, then if there's no negative cycle, like this one, I change the sign, so it's no longer negative. Now this is a positive cycle. Okay, all right. It turned out that if there's no negative cycle, then the shortest path is always simple. Okay, what does that mean? Remember, a simple path means that no nodes is traversed, is visited more than once in this path. A cycle is other than the endpoint, no nodes is visited more than once. Okay, so why is all shortest paths are simple? Well, we've seen this earlier for the unweighted graph. The reason is because that if you have a, let's say that if I consider this path is not simple because I visit the U2 more than once. Okay, that means that this path contains a cycle, which is starting from U2 and then come back at the U2. Okay, but if this cycle has weight bigger than 0, I could just remove it and only consider this purple path. Change the color. Only consider this green path, and it can only have a shorter way to reach from U1 to U6. Okay, so in other words, if you consider 2 nodes, if you consider a path which is not simple, okay, like this, then you can always remove that loop. That means you have a cycle inside. You can always remove that cycle and then get a shorter path, because the cycles, when you remove the cycle, because its length is positive, that means when you remove it, you're only improving the length. Okay, so you can always get a shorter one by removing the cycle. That's why that if we consider graphs with no elegant cycle, then the shortest path has to be simple. So from now on, when we compute the shortest path, we'll only need to focus on simple paths. Okay, we don't have to worry about the paths that may have a loop. Okay. So that's the first property of shortest path. All right, the second one, we also have seen this before when we talk about BFS, which is that this optimal substructure property, which is that if I have a shortest path going from U1 to say UM, so let's say this is shortest path connecting U1 to UM, okay? Then any subpath, if you take any subportion of the path, that has to be shortest as well, okay? So you take any subpath from UI to UJ, then this must be the shortest path connecting UI to UJ as well. Okay, and again, as not a short way to say this is that any subportion of the shortest path must be shortest themselves. Okay, so all right. Now this property is kind of important. We used this in BFS. It's important in general because what this means is that to get shortest path, if I already have some shorter shortest path, then longer shortest path essentially composed of concatenating shorter shortest path properly. I can extend shorter a piece of shortest path. I can extend it to get a shortest path to reach other nodes essentially. Okay. All right. Another property of the shortest path is so-called the triangle inequality. Okay. This is just like a triangle inequality in standard triangle that you in high school you learned. So what this is saying is that suppose I have an edge. Sorry, I have an edge going from Z to V. Okay, and let's say I have a path going from S So from now on, I'm going to use this delta UV to denote the shortest path distance from U to V. Okay, so this just means that the distance from U to V. So what this triangle inequality is saying is that the shortest path distance from S to V, okay, cannot be more than, so the shortest path distance from S to V is bounded from above by the shortest path distance from S to Z plus the edge weight of Z to W. Okay, so this is the edge weight of Z to V. Okay, so this is the edge weight of Z to V. Okay, this is natural because this is if this red one is the shortest path, and this is simply the length of the path going from S to Z and then from Z to V. Okay, so the length of this is the length of this path. Okay, obviously, since the dotted one is the shortest path, then this length has to be smaller or equal to this the path going from S to Z and then from Z to V. Okay, all right. Now, I'm also going to use sometimes if equality holds. Okay, in other words, if the shortest path distance from S to V equal to the shortest path from S to Z plus this edge, weight of the edge ZV. What does this mean? This means that this red path I'm drawing here must be shortest path from S to V. Okay, in this case, we say that the Z is predecessor of V along the shortest path. Okay, right? In other words, ZV is the last edge along the shortest path from S to V. Okay, so this is the last edge. All right,